get started. Yeah, if either of you guys want to talk about the midterm, you can come by my office anytime this week if you want. We went over that on Thursday. Okay. So we are going to talk about main memory. I'll probably post up a homework today for this chapter. That's not going to be due till next week since midterm fell in the middle of two chapters. The one last week was 10 points, and then this one will be 10 points. So that's kind of one assignment, just like the other two that we did. Okay, so we're starting something new. This is actually kind of completely different from what we've been doing. We're going to be talking about memory management. Memory management, this chapter 8 is broken up into two kind of major sections. We have like a little bit of introduction into the idea behind memory management, like what it's for, and why we need it, the problems that it's trying to solve. And then we talk about a few specific schemes, and there's a lot of different schemes to memory management. We're talking about operating systems and architecture. Memory management is actually a very big area of research, and there's a lot of different ways to do it. So there is a lot of different topics in here. So we're going to take a look at why we need memory management and some of the basic theoretical background, like swapping and the idea of how processes see the memory. That's what we mean by contiguous memory allocation here. And then some approaches that aren't used quite as often, like segmentation, and then we'll also see paging, which is very popular. But these are all kind of different approaches to how to manage memory. And then we'll get into some specific examples, both on the hardware side, like with the Intel Pentium, as well as the operating system side, like how Linux and other operating systems handle memory management. Because memory management, you'll find, is a cooperation between both hardware and software, both operating system and then architecture. So operating systems will usually adapt their memory management to whatever particular hardware they're running. So different types of hardware provide different services that the operating system can take advantage of. So let's go to the next slide. Okay, so when running processes in an operating system, one of our biggest resources is obviously memory. Okay, we've kind of been concentrating on our other kind of more important resource, which is CPU. Okay, so now we're kind of looking at the other big resource of running a process. So the idea here is memory is used for a few things. One is the actual program itself needs to reside in memory. So it's necessary to actually store the sequence of instructions that will be running on the CPU. Additionally, we also do things like store data and generate data that memory needs. Okay? So anything that we can't keep in registers or from step to step in our computation, we'll often use memory to store that data, as well as bring data in from the outside world, kind of from our program or from other external sources like I/O. Okay, so main memory and registers are the only storage the CPU can access directly. Okay, we've already seen a little bit of this with our examples of I/O. We don't directly work on input from, say, a disk, right? We'll ask the operating system to get data from a disk, and the operating system will pull that in to main memory, and then we can use our instructions to access that. If you remember back to any kind of real low-level programming like assembler and things like that, if you look at machine code does not have instructions for reading things outside of loading things from registers or things from memory locations. Okay. Now, we have a few issues here. One is we often have far more data, both programs both the programs themselves and their data. Then we have physical memory. Okay, that's one big thing that happens. And the other thing is we'd rather access things from CPU rather than from memory, even main memory, right? Because registers are a lot faster, and most of our operations happen from registers. Okay, so then we have this other intermediate stage of cache. Okay, we'll see that a lot of memory management kind of follows the pattern that we saw before when generally discussing cache. Okay, what's the idea behind cache? Okay, so we have a faster place that we hold stuff from main memory. So what are the issues there? It's usually small. Why is that? Yeah, cost is the main reason, right? It's expensive, right? So normally our cache is a lot smaller. Our main memory is a lot larger. It's way faster, right? And a lot slower. So how do we get the most out of our cache? What we'd like to do. For the CPU, and we want to load something into a register. We'll often look in cache first, but then what can happen then? It might not be there, right? If it is there, it's easy, right? You just pull out a cache and you load it into your register or whatever. Okay. If it's not there, then what problem do we run into? Okay, we have to go find it in memory and then do what? Bring it into cache. Okay, we'll usually bring it into cache and then we'll pull it from cache. Now, what's the issue with bringing it into cache? You got to kick something out, usually, right? Our cache is small. It's fast. It's expensive. Chances are we're using all of it, right? We'd like to be using all of it. Okay. So if we don't have something in cache called a miss, right? If we have a miss, we need to go to disk. We need to boot something out of cache, put the thing that we just looked for into cache, and then we can pull from it. Okay. We'll see main memory uses some of these same ideas, especially when talking about virtual memory, where we can swap to even further down the hierarchy to secondary storage. Okay. And then final issue is protection of memory. Okay. This is very important. We've already seen protection of the CPU in a lot of ways in our discussion of scheduling. Okay. What are some of the things that we ran into to kind of protect the CPU from users? What's the biggest one? What was the one thing that we, like when we were talking about locking and things, we said that we did not want to give user-level programs access to, for example, disabling registers. Disabling interrupts. Why is that? Right, like if you could turn off interrupts, you could turn off the timer interrupt that interrupts you and lets another process run. Right? Part of an operating system's job is protecting the rest of the users and the rest of the operating system from individual users. Okay? So we don't give them access to things like disabling registers. Same here with memory. We'll see that there's a lot of issues with the fact that we do not want processes to be able to get at the memory of other processes. Okay? Bad things can happen. You could be running computation, storing the results, and then another process could come in and alter those results. Okay, that's no good if you can have any kind of guarantees that you're the only one working on your particular memory area. Okay, so we have a lot of like management issues of managing the different pieces of memory. We have these performance issues, right? We want to get the best performance out of the the best memory we have at a given time. And then we also have some of these protection issues of we don't want multiple processes to be able to get at each other's memory. Okay. The first thing that we need to kind of understand is that often when talking about memory, okay, one of the biggest concepts we need to understand is that when we talk about memory, we talk about addresses, right? If you remember back to assembler, if you want to access something from memory, what you'll normally do is you'll load an address, right, a memory address, and then you can load that memory address into a register or do an operation on it, right? So the idea is you have to give the CPU some address to put in there, okay? Now, the simplest idea would be load a physical address, right, in memory. If you have all your memory in your system, you just start counting at 0. That's address 0 is the first byte, right? And then just count up until you get to the end of your memory. Okay? So, a simple program would just load one of those addresses in, go to that point in memory, and pull the pieces out. Okay? Those addresses of those physical bytes on memory chips on your computer, those are known as physical addresses. Okay? Physical addresses are the literal address of the chips in your hardware. Okay? Just right off the bat, what are some issues you can think of with that? The idea of if I were to write these programs using these addresses which represent the physical chips in my hardware. Hard to keep up with how? The programmer, it has to know. Okay, well, we can kind of do that just with the variables are essentially that, right? So we're going to need to do that either way. But basically, if I tell you you have a meg to work with, you can just dump your code and your data in that meg and know where everything is, right? Which is really how we used to do programs.
It's hard. It takes more time to find things if they're not.
You'll have that issue really no matter what. Because in other words, whether I use those literal addresses or something else, some things will be farther than others.
Is it double work getting the address and getting the byte?
We can't get around it. We have to somehow give the programmer some number to punch in so that it can get to a particular place. So see, the reason, like some of this stuff I'm saying is because no matter what we do, we can't get around some of those things. So I don't really see those as problems. I just kind of see them as the nature of programming. There is an issue with this keeping track of things but I don't know. It hasn't really been said in a way that's realistic. Okay, when I say, okay, you have a meg of memory, start programming. Okay, and you can start programming in that meg of memory, right? So you'll write your program, right? You'll say, okay, well, I need a variable. I'll take address 0, which isn't realistic because you probably have your code. But let's say we put our code somewhere else. Okay, so you'll say, okay, my x variable, that's the first variable I'm going to use. I'll give that 0, right? My y variable is going to be the next byte, so I'll make sure I store that at 1. Okay, we'll have a fancy compiler that makes it so we can write programs and talk about x and y, but it'll turn that into 0 and 1 or whatever the address is. Okay, and it works. Okay, I write my program, it goes through and looks at those variables, stores data in it, pulls data back, does some calculations. Okay, so, and it works for me. What kind of operating systems have we been talking about though? Is the operating system we've been talking about that simple? I'm going to sit down, I'm going to write my x's and y's and do some computations. Okay, so the first thing that comes up, there may be multiple people, which means multiple programs. Okay, so I write my program. I start with 0 for x, 1 for y. What does the next person do? Okay, so now we have an issue. They have to know all of the variables that I'm using, right, so that they don't use any of those addresses, right? Because if they write a program, if they run my same program, if they run the same program I'm running, both of our x values, our x variables, want to use address 0. Both of our y values want to use address 1. Okay? So now we all of a sudden, we already run into a problem. Okay? The other thing is, what happens when I get 2 megs of memory? Now what do I do? In order to use any of those 2 megs of memory, my program has to point out anything above the 1 meg at that point. Right? So these are the major issues that come up. So what do you think the general idea is to solve this? In between what? Okay, so one idea is if I have all my memory, let's say I have 2 programs, I can give each of them half, right? So, but what does that mean about my programming at this point? Can I still do the thing I was saying where I say x is at address 0, y is at address 1? How many address zeros are there? There's only 1, right? If I have chips in my hardware and I start numbering the addresses at the beginning, how many beginnings are there? There's 1 beginning. So what do I do? Right. I offset, right? I say, every time I say address 0, okay, if I'm the process that has the first half of memory, I can just say, okay, that's address 0. What's my offset? 0. I say address 0 is 0. Done. But if I'm the other program, I'll say, okay, start numbering at 1 meg. Okay? So now anytime you say address 0, instead of that, use address 0 plus 1 meg. The next one, address 1 plus 1 meg. Okay? So what we've done here already is that we've made it so that multiple programs can use the same addressing scheme in their program, but those might not be the same addresses that they use in physical memory. Okay? So what we have here is the idea of a logical address space. The logical address space is what we present to the programmer. Okay? And a lot of memory management is doing tricks with how we map from a logical address space that we presented to the programmer and the physical address space that's available in our hardware. Okay, that's what memory management is. Okay, that's what it's trying to solve. Because you'll see that by having a mechanism like this, we can take care of most of these problems. The first problem we've already solved of 2 people trying to write a program, they both want to access particular memory addresses, we don't want them colliding with each other. We'll see that we can also solve problems like virtual memory, having more memory available to the programs than we physically have. Okay? We can also take care of some of these issues with protecting programs from one another. Okay? So, the idea here is that we have some registers that can say things like give us an offset, which is this base. So instead of starting at 0, we go to this particular offset that's designated by the operating system. And then they can start using addresses from 0 to a particular limit that we give them. So in that way, what we can do is give them a little slice of this memory. Okay? What this slice means is if you can't go past the limit because you'll start encroaching on some other process's memory. Okay? You can't start addressing anything below the base. Okay? So the idea is, if we can do this, especially at the hardware level, that's even better. Okay? We can have the hardware load this base and limit and then start running instructions. We don't want to have to use the CPU to do all of these adding so much to a memory address before we access it and things like that. Because this is every memory access which will add up. So the more we can do in hardware, the better. So, if we have this idea of logical address space, okay, and we have this idea of the physical address space, and we have this idea of mapping between the two. Okay. Now we have some design issues as far as how do we do this mapping. Okay. And when do we do this mapping? More importantly. Okay. This concept of binding of instructions. Okay. To memory. This is that idea of when I start to use those, like in our example program, these variables like X and Y, right? Or even more importantly, the instructions themselves, right? Jump to this address or jump to that address. Okay? I have a problem because my instructions include numbers in them. Okay? And I need these numbers to be logical addresses that the programmer deals with, right? And then those numbers need to be something else when the actual instruction executes, okay, when we're running the program. Okay? So our first option would be binding these addresses that we're dealing with at compile time. Okay? This was the first example, the idea of a programmer just sits down and says X is at memory address 0, Y is at memory address 1. Those numbers are actually the physical addresses. Okay? We don't really do that anymore. Okay? They point out, like in your book as an example, they point out that DOS used to do that. Okay? There wasn't a problem with these old operating systems doing that because there was one program running. If you wanted to start at address 0, no one else was using address 0. So how do you do this this memory binding? Just pick numbers and start using them. Okay? Just make sure the numbers you pick were lower than how much physical memory you had. Okay? That doesn't work in modern operating systems. Okay? Another one is the idea of a load time binding. Okay? Load time binding, the idea here is when you're about to run the program, okay, a loader will go through your addresses in that program and map them to real addresses before it runs. So here the idea is we could do a load time binding with our example of having two processes running, and we want to split the memory between them. So we decide we're going to split the memory in half, and anything that the second process wants to access, they need to add 1 meg to it. Okay? Anything that the first process wants to do, they can use the literal address that they have. Okay? A load time solution would be when we're loading process 2, we go through all the memory addresses in process 2 and just add 1 meg to them. And that'll work fine, right? Because now when the program runs, it can use the literal numbers, literal addresses in there, and those will be the actual physical addresses they need to use. So the programmer still wrote to the logical addresses starting at 0, okay? But at load time, we offset all of them, and then that maps it into main memory, into physical memory. Whereas process 0, we don't alter any of the addresses, and it maps directly into physical memory. That's a load time solution. Okay? Okay? Most of the time, though, we'll be doing the more modern idea of execution time memory binding. Okay? Execution time memory binding means that our mapping of logical to physical addresses happens while the program is executing. Okay? What this means is that we also have the option of even changing the addresses in the middle of execution. Okay? This might not seem to make sense, that like if I'm running along in a program, why can't I just deal with some particular addresses that they're mapped to, right? But we've already seen that programs don't necessarily just load them on the CPU and run, right? We'll be swapping them in, swapping them out, moving them around. Some of them will be put in waiting queues. Some of them will, be preempted. Okay? Every time those things change, right? A process changes, we might need to change how it maps to memory. Okay? So we might be getting the first variable from a particular physical address, and the same variable when we get maybe swapped off and come back, that same variable might be a different place in memory. Okay? That's a difficult problem to solve, but luckily we have the hardware and software in modern operating systems to do that. That gives us a lot of flexibility. We can move things around while they're running. Okay. Questions on these three different styles of mapping from logical to physical addresses?
How it's defined? I mean, when it's supposed to be preempted, and when again it's ready to run, and comes back against this operand, and it's a different place. How does that happen?
We just tell it. We just say, it's dealing with some logical addresses. There have to be addresses, right? There's no way around that. So our instructions, our variables, they all need to be at addresses. Okay? The idea, though, is that they have logical addresses they deal with. So a program has the concept of 5 bytes from the beginning. Okay? From the beginning of the memory that I'm dealing with, there's 5 bytes from the beginning. Okay? I can make that 5 bytes anywhere in memory. All I need is a translation, right? I just say, instead of 5 bytes into memory, you need 5 bytes plus wherever I start you. So if you maintain a table that says, instead of 5 bytes into main memory, do 5 bytes plus 1 meg. That's a mapping. Does that make sense? Okay, that's a mapping. The trick is, how do we maintain that table? And how do we make it so that we can change that mapping potentially even while we're running, or when we're loading, or at compile time? These are different times that we can do that. We can decide on that mapping. How we do the mapping, though, is, I mean, that's another big question. Okay, any other questions? So, mapping from logical to physical addresses. Okay. This multi-step processing of a user program, okay? This is actually a longer kind of life cycle than we might normally think, okay? Hopefully we don't always think of it because we are programmers, right, as computer scientists. So we know that programs aren't born or anything like that. They don't appear out of nowhere, right? They're written, okay, we write source code, okay? Next we'll usually, for most languages, we will compile them, right? Once we compile them, they'll become basically machine code, right? Or here they're calling them object modules, okay? We have some other steps that normally we don't concern ourselves with because the operating system normally automatically handles that, okay? But since we're talking about operating systems, we need to see what goes on there. So the first thing is the idea of a linker loader, okay? A linker loader has multiple jobs. One of them might be to do this idea of mapping addresses already if our addresses are mapped at load time. Okay? This isn't common in most operating systems. We don't normally do load time address mapping. But if we were, the loader would be responsible for that. The idea here is the linker loader is responsible for getting the actual code that's going to run on the CPU essentially off disk and into memory and ready to run. Okay, so that the CPU can start pulling instructions up and executing them. Okay? It's also called a linker in the sense that most of the time our programs, we don't necessarily have to write all of the program. Okay? We often use very convenient mechanisms of things like libraries. Okay? Libraries come in many shapes and forms as well. Okay? And how we link the libraries in is also another one of these decisions of whether we do it at compile time, load time, or at runtime. Okay? So let me go over that briefly, the idea of using a library. Because we have to start thinking of programs in this sense of a sequence of instructions. Okay? Because before we were just thinking of them as, you know, things that run on a CPU, right? They just kind of, we were more concerned of they're running for this time and not for that time, right? We'd be running now, but then we'd swap out and then something else would run. We're concerned with a completely different aspect now. We're not really concerned with how long, you know, over time. We're really worried about what does a program or a process mean in space. Okay, what I mean by that is where do we actually keep all that code? Because we're not quite as concerned as which instruction we're on as we are on where is that code sitting right now, and where is the CPU going to get it. Okay, so the first thing is, if you're running a program is nothing but a sequence of CPU instructions, right? Okay, it's not even code anymore, right? Before we were writing code in our nice language like C or whatever, right? C or C++, or I don't want to get into Java, but that's another complicated step. But like C or C++, for example, we'd write code that would turn into machine code, right? Machine language, okay, which is just a sequence of individual instructions. Okay, this sequence of individual instructions, a CPU executes that by doing things like having an instruction pointer or a program counter, right, that says, okay, I'm on instruction 1, now I'm on instruction 2, 3, 4, 5, 6, right? And it just walks through, it might branch and jump and whatnot. Okay, so the idea here is that we have this code in memory. We need to load it in. We need to have this point to the right place in memory. Okay? Now, the problem is this gets more complicated, okay? Because this might be my program. This might be the program that I wrote. But I might use libraries, for example. Okay? One problem that we run into is that if we're using a library, what is a library in program? Right. So like if I'm writing a new program, I might use code that's already written in a library. A library is nothing but code that someone else has written, or maybe even that we've written, that we put together because we want to reuse it. Okay? So let's say I have a square root function. It's nothing but a sequence of instructions as well. Right? Well, normally, if I want to run this, we can do something like a jump, right? We can jump to the instructions in here, and when it gets done with the square root function, it can jump back. Problem is where do we jump? If I want to run square root, right? Square root here. Can I just put in square root? No. Because this is machine code. Machine code is jump to an address. Okay. Well, to jump to an address, I need to also load square root into memory. But I didn't write it. It's a library that's available to me, right? So I need some way of getting this into my memory space, right? The square root library function into memory space, and then this square root address that's written needs to point to the beginning of that function, right? So, and then I don't want the programmer to have to write something that loads it into memory and then accesses it, right? So the idea is that a linker loader would do that. It would be in charge of getting the appropriate library, pulling it into memory, and finding out where you call that library and saying, hey, this is where you jump because I went and found it for you. Okay? So, and there are multiple ways to do that. Okay, sometimes it's static binding, sometimes it's dynamic binding. Okay, static binding means that it needs to be mapped into your address space at a particular point because you've written your program to jump to a particular place. Dynamic loading is more, I'm going to jump to this kind of pointer of where square root is, but I need you to set the pointer to wherever you decided to load the dynamic library. Okay? So that kind of stuff happens right here. It's where we combine all, the loader stage, the linker loader stage is where we combine all of the code together so that we can start jumping through instructions. Okay? And then we get to runtime, okay? And at runtime, again, there's an aspect to this where we do some of this library idea, and that's on dynamic libraries, which is not done during load time. Okay? But at runtime, we still have that issue of if we have the capability of moving things around while they're running, this mapping problem of logical to physical addresses still occurs in there. In more simple operating systems, we might, all of our mapping and everything might stop here. Okay, and our even more simple single process, single user operating systems, our mapping might get done even before linking loading. Or at least before linking. We always have to load. We always have to pull it off disk and put it in. Okay? So any questions on this diagram here? This idea of, these stages. Okay, these stages occur in time, and those times, are different styles of doing some of this mapping. Okay. Any questions on this idea of libraries? Libraries are just a way of popping in additional code into your memory space so that you don't have to rewrite it. Okay? Whereas you'd normally write those instructions, it's going to be loaded from a library, and then you can just step through their instructions.
So when you first started, you just say that when we use the library, it's a runtime, compile time, or definitely not compile time.
No, you can do static linking
Well,
at compile time. But see, we hardly ever do any memory mapping at compile time. So the idea of compile time is you get a static library and you actually pull the code into your program. So your program will, I don't know if any of you have really looked at programs that you compile. This usually happens on Unix more. You might write a small piece of code like a hello world, and then you compile it, and it's actually big. It's like you wrote 3 lines of code, and after you compile it, it's like 100K, like for your program. Sometimes that happens. The main reason that would happen would be a static linking. That's a compile time linking. What happened was you put in printf hello world, but printf is hard. Printf is a lot of code that it needs to do to go through and print to the screen. So what it did was it went to the library, got all the code that it needed to do print, for your hello world. It got all that code and brought it over, arranged it on disk into your program, so that now you have all the code you need. You can load that whole thing into memory and run it.
Yeah, that was my question.
Okay, that's a compile time linking. Okay, you can also have the idea of you write hello world, which is a little tiny piece of code, and right when you're about to run, the operating system goes and gets all the stuff for printf, puts it in above you, and then you just run your little piece of code which jumps to those pieces.
In that case, if I just like the Unix program, as you get that in that case, when actually the program is running, there doesn't need to do any kind of mapping or anything. So the part I ask requested from the library, well, compiling it's already now in there. So
You don't have to do any loading because you've loaded it with your program.
no, I'm talking about mapping.
You always have to do mapping. Always. No matter where you get that library function, it's instructions. Those instructions have to sit somewhere in memory. You can't just start popping them into memory, you have to map them. In other words, you can't. A library's code is no different from your code.
Yeah, but if it's already, after compilation part is already inside my program, which I wrote, and the part I took from the library already in there, then when I run it, I don't need that part anymore because it's already.
You don't need a linker like this. You're already linked.
I mean, it's just not copy that part inside the program?
Yes.
Like when I said print
In other words,
F.
there's not two blocks here. There's not this part and then this part. It's all just one big block.
Right, that's what I
Okay. But you're still mapping. I just want to emphasize that. Don't say you're not mapping. Because no matter what, if you're using memory, you are mapping. There's really no difference between using a library that you compile into your program and one that's linked, except for, the one that's just linked, except for this idea that instead of you copying the block of the square root to the end of your program, the operating system does that right before you run. It goes and finds the square root function, puts it at the end, and you jump to it just the same as you would. You see what I'm saying? That's a linker. That's a linker loader is what they call it. Okay? So the idea is that you wrote this big, long program, but you can think of it as it was broken into pages. I don't really want to use the word page, but it's broken into chapters, let's say. Okay, you have chapters which have, stuff like square root is a chapter and things like that. Okay? One is you put one on a bookshelf so that other people can also use that chapter in their book. Okay? And then when you're about to run, you go grab it, put it on, and it runs. The other is no one else gets to use this chapter. I'm putting it directly in my book, and then I just run it directly. But notice, nothing changes about how your book looks. It's just a matter of whether you left it on the shelf before you started running or not. Okay, that's a linker loader, whereas you're always mapping. In other words, how you run through the instructions are the same. Oh, yeah.
So, if I want to use that library, it has to be in the same block as the rest of my instructions.
Yeah, as far as the CPU is concerned, yes. Okay? There are additional tricks that we do that take this kind of sharing even further, but the idea is that it must be in your memory space in some way, unless you're doing something along the lines of asking the operating system to do something, and then the operating system goes and does it outside of your memory space. Like system calls are like that. You actually say, hey, operating system, go do something, and it will go do something outside of your memory. But normally, we are running through the code ourselves. So if we're running through library code, or we're running through code that we wrote, it needs to be in our memory space. It needs to be in our view of what memory looks like. All right? Our jump instructions, our load instructions, all that stuff. Okay? The reason I hesitated a little bit there was the idea that operating systems can really do neat tricks with like libraries that a lot of users are using. What they'll do is they'll actually take sections of your memory and make them shared among a bunch of users, and you don't even know. Okay, the advantage of that is we'll see that we can actually map more than one logical address space to the same physical location, which is nifty because you can end up saving a lot of space. Okay. Logical addresses and physical addresses. Okay. Logical addresses, they say generated by the CPU, also referred to as virtual addresses. Okay. The reason they're saying generated by the CPU is because it's a trick that the CPU is doing. It's letting you see particular addresses that have a particular relationship with the chips that are on your physical hardware. Okay, they say it's generated by the CPU because when you say address 0, the CPU is kind of putting up a front and saying, oh, okay, I'll take your address 0, but then behind the scenes it's going back and messing with it and then accessing a completely different physical address. Okay. This is a good point here, this compile time and load time address binding. Logical and physical addresses are the same. In other words, at compile time or load time, you actually go through and change the addresses of your program to their real physical address that they're going to use. Okay, so in that case, like I said, they're very similar. It's just a matter of whether you do it right when you're about to run or when you're actually writing and compiling the program. But either way, they're going to become physical addresses. Okay, that load time idea, that opened our doors to the example we said where we might split the address in half and then do an offset, right? At load time, we'd go through and change those addresses, but they'd still be physical addresses. Okay? At compile time means that you actually add the 1 meg or whatever when you're writing and compiling the program. Okay. A memory management unit. Okay? Like I said before, a memory management unit, we don't want to be doing this offset and limit and all these things that we were talking about. We don't want to do this with the CPU directly. I mean, when I say we don't want to do this with the CPU, we don't want to run instructions to do this. Okay, we don't want to add and all that stuff using the CPU to do this offset. Okay, typically our hardware, or even the chip itself, will have memory, will have hardware dedicated to all of this mapping. Okay, and memory management unit is something that we can present it with a logical address, and it will either give to us or to the CPU, it'll give a physical address. So we can kind of approach the MMU just giving it logical addresses, saying I want to execute this instruction accessing this particular memory address, and it will automatically translate that address to something that makes physical sense and then run the instruction with it. Okay? An MMU is a way for us to run our programs at high speed using all of these logical, nice looking addresses, even though behind the scenes they're going to all different areas of physical memory.
If you run GDB,
Mm-hmm.
does that actually show you the
No.
physical address, or is that
No,
still-
not in a. It can get at physical addresses, I believe, but normally when you're running through GDB, you're still seeing logical addresses because the program never sees the physical. In other words, the program's actually presenting the addresses to the memory management unit using the logical addresses. Because like GDB, for those of you, GDB is a debugger. Okay, it's a way that you can kind of step through programs or inspect what a program's doing, mainly for fixing bugs. So in modern operating systems like Unix or whatever that you're running GDB, like Linux, where you'd run GDB, you're presented with just 4 gigs, just straight up, and that's in 32-bit operating systems. You'll find that 4 gigs is 32 bits, okay? So that's why, so in a 32-bit operating system, you get 4 gigs of memory, and you can do with it whatever you want. You just walk through it, you can load data and stuff like that. GDB just sees that. It's just a way of looking directly at that memory, okay? But still, behind the scenes, your 4 gig, first of all, doesn't exist, right? You don't actually, chances are you don't have that much. Well, with swap maybe, but chances are you don't have that much memory, but they're counting on you not using it all. But and the other thing is it's not necessarily in your main memory from byte 0 to 4 gig. Okay, some of it will be on one page. So the rest of it might be on a page that's even earlier than that. So it's scattered all throughout physical memory. Okay, so the idea here in this diagram is just drawing out the idea of some piece of hardware that when you pop in logical addresses, physical addresses come out the back. Okay, and they're showing this complex circuit of having a register that holds the offset and addition, right? So they have addition here showing that we can send in an address like 346, adding 14,000 to it will give us 14,346.
That's a real.
Yes, that's the physical address you see there is if you went to the chip, started numbering at 0, going all the way up to 14,346. See, that's what we need to get to. Because that's really all the CPU understands. Right? The CPU needs that address. But you don't want to use that address in your program, even with a compiler, right? You don't want to have to know that that's how far up you are, and it might change. Okay? So we need this layer in between, but we don't want a little adder circuit for every single address that we're going to pump into in here. So we need some good way to do this for every address that's in memory. Yeah.
So the logical address is 347. This is going to be 14347.
In this case, yes, we have one. This is a simple offset memory management unit. Depending on how we manage it, though, it might not be 14347 because one of the steps that might come in here is changing the relocation register.
Because in computer architecture, that's where I get a little idea of these things.
No, it normally will be 14347 because you don't.
Different places. Actual memory is.
The thing is if you have two addresses right next to each other, chances are they're right next to each other in physical memory. You do not want to deal with memory management on a byte-by-byte basis. It's impossible. Okay? Your chances are you're going to be using blocks, okay, what we call pages. Okay? So, logical address 347, chances are it will be 14347. Okay? When I say it's scattered about, really blocks of these addresses are scattered about. But normally from 14,000 up to, depending on how big your pages are, let's say 14,512, will all map to the same area of physical memory. Okay? But the next address, like instead of 512, 513, 513 might have a completely different relocation register. Okay? So, dynamic loading. This is what I was talking about briefly, the idea of mapping these memory addresses right when you're about to run. Okay? And in fact, even more than that, it might move around while we're running. Okay? Dynamic loading can often be even more clever than this. Anything like that, that's with these diagonals is something I wrote. Okay. Color the other way. That's something someone else wrote. A library. Okay. Now, we can load it at compile time. Okay, that means when we're running our compiler to generate our machine code, the compiler will go out, grab the library code, tack it on. Okay, and then this is our executable. This whole block is our executable. We wrote the part that's diagonal, they wrote the part that's solid. Okay, this whole file, we can go shove it to a CPU and have it run. Okay, it can jump around between our code and their code as we run. Okay. So, that's nifty. We compile everything, we take the whole executable, we run it.
Okay, suppose after I compile, I don't want to run the program.
You can.
After I finish compiling, I don't want to run that one.
Okay.
So what happens, that block still sit down whole block?
It's a block. One byte after the other. On disk, one byte after the other. Done.
I mean, after compiling, it's say like a class file, suppose. It's saved. And I'm talking Java sense. Then that block part, which is the library part, is still inside that class file. You understand what I'm saying?
Okay. Java would not do any compile time binding whatsoever.
It's
Java
not
so
It's
far
like
never
any other program than Java.
What I'm saying is, okay, if you want to talk about it, I mean, in whatever terms you want, it's with it.
That's
That's all there is to say, is that if you were to go in there and look at the bytes in that file, the next byte would be the first byte that you see in the library function.
Okay, now I have a second question. Okay, it's there. Now, when, say like 2 days later, I want to run the program, and in that directory, the main library is not there. Is gonna run?
It's sitting right there next. If you take two things, you put them together, that's what it is. I mean, don't overthink. This is the easy one, okay? You need to be asking questions when we get past. This is just, you take them, you literally put them right next to each other. That's one file, okay? The hard part is not this, about where the file, the hard part is that inside this diagonal part, there are instructions. There are instructions that want to use code in there. The hard part is that we have to put addresses in there that can jump to back and forth. But that's not hard. You just say, find out where it is, and wherever you see that address, you just go through and put in that number. Okay, that's what computers do well, right? Is keep track of a bunch of numbers and write them in. Okay? So this is compile time. We still do this today. This happens if you use what's called static libraries. Okay? Now, there's load time. Our program looks like this, right, with the diagonals, by itself. Right before we run, or while we're loading, we put this into memory, we take the library file, load it into memory right after that, and then run. Okay? This is almost exactly like compile time. The difference, compile time, on disk, the whole program was sitting there, right? At runtime, think of it like this. We build that same file in memory. Okay? So we load our code, and then we go grab the library and put its code above it, and then run it. Okay? Dynamically loaded libraries are even kind of more removed in that the library code might actually be somewhere else in memory, and then we have little kind of pointers that the operating system can map to those places in memory. Typically with dynamically loaded libraries, we actually do tricks so that another user program can actually use the same code in memory. Because the operating system knows that these are the same library between them. Before it was kind of cut and paste. The operating system didn't see that library code as an entity. But now the operating system, it knows that that library is an actual thing on its own, right? That it's actual useful code on its own. And it can actually put that into memory that both of the programs see. Okay? What it actually ends up doing is giving the program kind of a ghost image of the library, and every time it jumps into that area, it actually goes to the shared hardware. Okay, that's the idea of dynamically loading.
In the first example, where you had them together at compile time, were they together and then they were compiled?
The compiler kind of compiles your stuff. It needs to take into account both. A compiler's job is to kind of see what the memory will look like afterwards and then puts in all the numbers. So it kind of says, well, you're this big. I know this library is this big. So those numbers need to be this particular offset.
I guess my question is, I'm not really seeing the difference between putting the two files together at compile time versus at runtime.
I mean, at load time, there isn't much difference.
Okay.
It's just a matter of whether or not that library is there with you. And if sometimes the loader can do some additional like tweaking as far as those offsets when it loads it, like if you have a different version or whatever. There isn't much difference. But that's why they were saying that the addresses you see in the programs are the same whether it's load time or compile time. Okay? The big thing here is that the memory management doesn't really have to do anything for those load time and compile time. But it does have to do some mapping, this not mapping to physical memory, but actually finding out where the code is, which in turn will get mapped to physical memory. Oh, sorry. This dynamic loading versus dynamic linking. Okay, dynamic loading is what we were talking about with the load time. Dynamic linking is this stuff. Is this pointing to a shared piece of code. Dynamic linking is by, like on Windows, you have a bunch of DLLs. DLLs are dynamically linked libraries, which is this. It means that you can have this piece of code that's separate and the operating system can share it among.
But they're compiled, right?
All of it's compiled. All of the things we've been talking about are compiled. They're machine code. Yes, it's compiled.
So like when DLL comes to the program, like say it's Microsoft Word, so those DLLs already been compiled with the executable and everything, right?
No, well, DLLs don't have to be with the executable when they're compiling. That's kind of their trick. You're kind of, chances are the developer had had a DLL that they used to build their program, but one of the tricks of DLLs is you could actually be running a different version when you run, on a different, if it's backwards compatible. In other words, the DLL you have might be different from the DLL that the developer had. Yeah. That's the trick. The trick is the fact that you're actually pointing to these symbols instead of addresses. And the operating system's doing the trickery as far as where it jumps.
Windows, right?
Absolutely not. Windows did not make up dynamic linking. No, most modern operating systems have dynamic linking. They're .so files on most of your Unix if you're like on a Linux system or something. Those .so files you see there are like DLLs. Shared object file versus dynamic linking. Okay, but most operating systems will have this. Modern operating systems will have this mechanism of dynamic linking. Dynamic linking is a big deal. I mean, just by the fact that we run machine code that deals with addresses, the fact that dynamic linking can go in there and kind of take these symbolic calling of. The idea is that you'd have like actually square root, if that's one of your functions that you call. You have a symbol for square root that the linker loader will go and find and replace with the addresses that you need, as opposed to an address. All right, so that is linking. and loading. Let's take a break, and then we'll talk about allocation of memory and swapping. Yeah, about 5 or 10 minutes.
You have a little pick me up there.
What's that? Oh,
Shocking.
like that.
I have to do a database research paper.
Uh-huh.
Do you have any ideas on
Any
what's-
way to combine that with...
No, I'm not worried
Oh.
about that. I don't have any idea like what's interesting and what's worth reading about. Do
Oh,
you have
wow.
any suggestions of something that
I
I
mean, it
could
depends
actually
on how-
handle?
There's
Basically,
actually
we're-
tons of like actually theoretical stuff. I didn't even know this but I took Sundaramen's class once. That had tons of stuff. I mean, there's one neat thing these days I think is distributed databases. You can look at a lot of data mining stuff. There's a lot of data mining material on like I don't know what area that would be in. Computational intelligence has a lot of data mining stuff. But do you have to do something just on any?
I think basically
Database
it's a
topic?
survey. She wants us to read 5 papers and kind of summarize.
I do some keywords on like. Are you gonna be doing bioinformatics stuff?
I haven't planned on it, but
Because there's neat database stuff in bioinformatics, like with the like protein databases and stuff. Like they do kind of data mining type stuff where
Isn't that like 5th semester here, 4th semester?
I don't know. Like there's regular databases where you like do queries and stuff, and you're exact, and you say, I need records that match this or that, and
Right.
they'll come up. And then there's like data mining where you actually can't just search on exact things. You kind of here's generally what I'm looking for, and I'll use statistics to find out whether or not results are good or not. So, like for example, we do a lot of stuff where you might search for a protein. You'll kind of give like a protein sequence, and it can go search through the database for proteins that are similar.
like degrees of what's it called?
Well, we do stuff like where you do like you'll go through the database, you'll compare your sequence to another sequence using like alignment and stuff, and then you'll calculate, their statistical p-values to say,
Right.
well, compared to random sequences, this is how statistically significant our match is,
Right.
and then you can return those results. So that kind of idea that's real.
I might do that.
There's actually tons of database-oriented stuff in bioinformatics just because of all the like genome information and protein information. So I mean, if you have to do something on databases, I'd probably look at that just so you can start getting familiar with bioinformatics to see if you
Yeah.
want to look at other stuff there. But there's that. There's one of the things that we've been doing lately in our group is even structural alignment. So we're getting into like the 3D structured databases, like these databases of like coordinates of atoms and stuff. Like you're trying to search for things that look similar. There's tons of like knowledge mining stuff, database type stuff with like clustering and.
Can you use that big computer for a second?
Oh yeah, sure.
Doesn't matter. Not the same class.
But
I might look into that.
outside of that, I don't really know anything about databases except for the theoretical stuff I did with Sunaraman, and that stuff's just not something you want to do as like a little project.
Yeah.
Like he sat there and like talked about negation for like 3 weeks, like on just like search for things that are not this. Is apparently a huge problem for.
Really?
Well, yeah, because it's the idea that you can't match on not something. You have to,
Right.
because there's like a whole universe of things. You have to match on. You say not one. That's the whole universe of things that aren't one. So you have to have the universe. You have to bound the universe, otherwise it's infinity. And it gets scary.
I see.
So like that's the kind of stuff that. So I mean, there's tons of like rich theoretical stuff. It's out there. What else do we do?
I just get my girlfriend to do it. She's
Oh, she's biostatistics, right?
NMR spectroscopy. That's her PhD stuff.
What is it?
NMR.
Oh, okay. Oh, the
Like
magnetic
matching.
resonance or
Yeah,
whatever?
right. Matching, I guess, chemical, identifying the peaks in a spectrum,
Yeah.
identifying different chemical compounds or whatever.
Yeah, I just look for any of those big kind of, because I mean, any of those big data sets that they do, they'll usually have some sort of nifty data mining stuff with it. And database stuff usually is happy with data mining stuff. So there's tons of stuff there. I mean, it's getting more interesting just because, you know, like in old school databases, it was all just SQL and logic programming. It was like big.
Right.
It was like even more exact than like before database guys were even more exact than non-database like programmers and stuff. Like we'd be writing, you know, hacking stuff out with C. They'd be writing like Prolog, like which are basically mathematical proofs that are programs. So they'd be sitting there doing all this stuff, and it would all be exact. But now it's funny because like all the database guys are going to like data mining and doing stuff like fuzzy, like, you know, all this soft computing stuff, learning neural nets, fuzzy logic, all that stuff. Where they go and I don't really know what I'm looking for. I'm kind of looking for this, and
Yeah.
it goes through and kind of guesses. It's pretty neat though. So there's tons of stuff.
It's a long way, I guess.
Zhang's group does a lot of different data mining stuff because he does all the computational intelligence stuff.
Wow, that's a lot.
So there's some stuff there.
42 megs. What's the max space on Gmail? Do you know attachments?
I don't know.
Huh?
2 gig probably.
No, not space wise, as in like attachment wise. Come on, work. Oh, attachment.
Just wait, it's uploading. How big's the attachment?
48 megs.
48 megs.
Yeah.
Yeah, it's gonna take a while.
Should take that long.
It
Cool.
shouldn't take that long.
School's network's what, like 2,000 kilobits a second? Good luck to him.
You shared space on the Novell from
It's
your
drive?
school account, right?
It's 10 megs. 20 megs? They increased it. Still not enough though. Well, this should work. Like, I don't know. Let's see.
You have a thumb drive?
I don't have mine with me. Yeah, I freaking need it. Yeah, they don't even have it on. I'll have to log on to mine. This should work at least. There we go.
Okay. We're going to just talk a little bit about swapping, and then we'll be done for today. Swapping. The idea of swapping is to be able to use our secondary storage. Our secondary storage is disk and whatnot, right? The idea behind swapping is being able to use secondary storage as a temporary place for storing main memory information. Okay, so secondary storage is to main memory like main memory is to cache. Okay, it's a backing store for the real thing like memory cache. Okay, so a process can be swapped temporarily out of memory to a backing store and then brought back into memory for continued execution. Okay, just like the CPU cannot access anything that's not in main memory. Okay, it even more. We can't be executing code or accessing data that's on secondary storage in the backing store. Okay, so what we have to do is before we can do anything like execute instructions is we need to copy things back. Okay, so the idea is when we're not using it, you copy stuff that's in main memory down to disk. Okay, and right before you need it, you pull it back in, and then you can deal with the memory, with memory via the CPU, run instructions and everything like that. Okay, so this kind of sleight of hand, okay, needs to be very, very efficient so that we can get decent performance considering because the backing store might be very large, but it'll also be very slow, even more so than the difference between cache and main memory. Okay, so this priority-based swapping, just different approaches to doing swapping. We kind of mentioned briefly, we didn't really go into any detail, but there was the idea of like a long-term scheduler or a medium-term scheduler when dealing with processes. Okay? One of the things that something like a medium-term scheduler, we mostly concentrate on short-term schedulers, which are getting a process that we can put on the CPU and running it. Okay? Medium-term scheduling can do things like choosing certain processes based on how much of the code that you need is already in main memory and not in swap, or making decisions on whether you should make something go down to swap instead of being in main memory. It's something like a lower priority process will probably have a higher likelihood of being pushed down into swap to make room for higher priority processes in memory. Okay, so that's a big issue here with doing tricks like swapping. Major part of swap time is the transfer time. Okay, what they're saying here is that when we get into memory and memory mapping, okay, the transfer time on memory is usually very fast, like from memory to CPU, okay, even faster between cache and CPU. Okay, when your access times and transfer times are so fast, the thing you're worried about is the overhead of doing all this mapping, right? Of this translating from one address to another. Okay, that's a really significant amount of time. With swapping, the transfer time from disk to main memory is so slow that the overhead, the time that it takes for you to map between the pieces of memory that are on disk that need to go back into memory, the time you decide, well, I need to copy this piece of disk up to main memory, all that time is insignificant compared to how long it takes to actually copy. Okay, because the transfer time is so slow compared to how fast the CPU runs. Okay, so that is a significant problem with swapping. Is you have to copy bulk data from disk into memory. Modified versions of swapping are found on many systems. Modern operating systems, we typically still just call it swapping. Okay, swap file or virtual memory. System maintains a ready queue of ready-to-run processes which have memory images on disk. Okay, yeah, we've seen this in our running. Again, this is kind of more a medium-term types of strategies as opposed to our short-term strategies that we concentrated on when scheduling processes. Okay. This is just showing you that you can swap, you can copy stuff in and out of memory. One thing about swapping that's interesting is programs that sit on disk. Okay. When you have a program on disk, these instructions that are in here that we run through using a program counter, essentially what you see on disk is, for the most part, it's not always the case, but for the most part, what you see on disk is what gets loaded into memory. Okay? What's on disk is kind of an image of what needs to be in memory so that you can start running. Okay? What's interesting about that is this. Typically what we'll do to use memory is we use what are called pages, which are just blocks of memory. Okay? So if I have some main memory, and let's say it has some pages like that. Okay? When I copy this program into memory, what I'll do is typically take a piece of it and put it in there. Okay? Through trickery, I might be able to even, take some pieces and not put them right next to the other piece that I copied in. And I might even put them out of order. Okay? The idea behind swap is that I can simulate more of this physical memory by just pretending like the backing store are extra pages of memory. And then I can just copy a page down and sit it on disk, and whenever I need it, I can just copy it back up. Okay? What's interesting about programs is that, let's say I need a page of memory that the program's sitting on. Okay, so the one you see here is the third page of the program. Right? So, let's say I want to use that page. So what do I got to do? I got to boot this one out, right? So I need to, typically what I need to do is take that page and copy it down to swap, right? What do you notice about this page in particular? This page with the program in it. Well, it is out of order. But let's say I need to kick it out. Okay, so what should I do? Should I copy it down here? I can copy it down there, right? And erase it from main memory. Okay, then when I need it again, I could take a free page in memory and copy it back up. So now it's back in memory, right? Does anybody see a more efficient way to do that? There's a trick. Let's say I need this page that I've just copied that into. Should I copy it back down here? Huh? This is the hard drive.
Oh, that is
This is hard drive. This is memory. What's that?
You just copied it to memory, right?
I just copied it to memory.
Yes, what? If you need it, why don't you use it?
Well, I did use it, and then now I need this page again. So I need to kick this out.
You keep it in main memory, just move it?
No.
Oh, okay.
I ran out of, I need this page. I have to boot it out of memory.
What's something that has been used for a while?
This is my choice. Okay, I've gone through all the things of this is the best page to take out.
I think it came from the hardware.
Okay, so what I'll do is, before I boot that out, I'll copy it down to this. I'll take it out. So I need it again. So I copy it back up. Got a free page. Okay. Now I need to boot this out again.
Well, what about
I'm telling you which page is it. You know what? That's the most critical. If that goes out of memory, a heart patient dies. Alright. So, yeah, this is an exercise of you guys can add more memory. Okay, this is an exercise of do you notice anything that's going on here? Okay, I need to use this page. This is the program, by the way. This is the program that's running.
It's wasting time. Like, can I just run it off hard drive? Isn't there a possibility? And like,
Absolutely not. Okay, if you wanted, that CPU would be horrible. Okay, I copied it from here, I copied it from here, and I copied it from here. What can you tell me about this data? Sorry, the data at the top page, the next page, and then the original program. They're all the same. This is the program.
does the program change every single time?
No,
It doesn't change.
it does not. What changes in a program?
Variable memory.
Data. Remember before we talked briefly about how a program looks? You have what's called text, and then you have stack and heap, which grow according to need. What we're talking about is text. Text doesn't change. If text doesn't change, you don't do any of this copying down to disk. Anytime you need to swap out text, you throw it away. Then where do you go every time you need it? Back to the same program.
So where's the program again? Is that
On disk. But that's a file
Right.
sitting on, just like you see when you're running a program, right? It's sitting there directly on disk. But the idea is that what's running in that program is an image of what needs to be in memory. Right? So a neat trick to do when swapping is that anything that doesn't change, okay? This can actually happen with data areas as well. Okay? What you do is you check, do I have a copy already in swap or from the original medium? Do I have a copy of that already on disk? Because chances are we don't need to erase anything that's in the swap. Right? Because there's tons of swap. So what you do is you check, did I already write it to disk somewhere? If I did, I can just toss this page out if it hasn't changed. Because I can always just copy from that other copy I already had on disk.
Because when you were copying it to the swap, you basically got two copies of the same thing.
Of the exact same thing. Now, that's very important if it changed. If it's not the exact same thing, you have to copy it to swap. Otherwise, you're throwing data away. Okay? But there are tricks to that, too. All you do is if you ever modify something in memory, you just flag it as dirty. As something that we've modified. That's the typical technique. And then, if something's dirty or modified, then that means that when you're swapping it out, you definitely need to copy it down. Okay? All right. We're getting into different mapping schemes. We'll save that for Thursday. But yeah, you might want to take a look at some of the things in your book. These mapping schemes are pretty. I don't know. You either get it or you don't. As far as like, if you get the idea of memory mapping, all of them make pretty good sense. Okay, but they are a little bit involved as far as the different schemes and the pros and cons to the different schemes. Okay, there's a lot of ways to map memory. Okay, so I recommend before Thursday you take a look at some of the material in the book, so you'll kind of have at least a ballpark idea when we get into the different techniques, not really algorithms, but techniques. Okay, so any questions on the general idea of memory management? So what we kind of covered is the major kind of responsibilities of memory management, and then we'll see some specific techniques.